Okay, can you hear me? Yes. So I'm presenting Higgs results on behalf of Atlas and CMS. And so briefly, I will describe the data sample collected by Atlas and CMS, then how standard model Higgs boson production works at LHC, and I will discuss the diboson channels that allow to, for example, to measure the mass and the width and CP and spin. Then I will talk a bit about di-fermion channels, decays, and then about cross-section, branching ratios, couplings, and a bit of prospects. So, okay. Basically, all these measurements are based on the Run 1 data set that has been collected in 2010, 2012. And the total luminosity is basically 6 inverse femtobarn collected in 2011, and 23 collected with ATV center of mass energy. The 6 were with 7 TV, and this is the delivered luminosity. The collected by single experiments is a bit lower, of course, due to experiment efficiencies. So before going to the Higgs, these are other measurements of standard model cross-sections done at LHC. You can see that we go from total cross-section to jets. Here we have W and Z's with and without jets. Then you have here TT bar, for example, and here you have Higgs. So these are all, and here are basically dibosons. So these are all measurements that have been done, in this case by Atlas. You have something similar from CMS, and compared to theoretical predictions. And this show over a very wide range of processes and cross-section how more or less well we understand the standard model. So we have a very nice picture of all the processes that are happening. So this is good to understand backgrounds and so on. Okay, so going to the Higgs boson production. Higgs boson production occurs basically through these through different processes. The highest cross-section is from the gluon-gluon fusion, that is this one. Then you have what is called vector boson fusion, in which that is this one. This is characterized by having two jets with rapidity gap in addition to the Higgs in the detector. Then you have associated production of Higgs and W that has lower cross-section, is shown here. Or it can be W or Z, of course. And finally, the TTH production that has low cross-section. So typically, uncertainty on the theoretical predictions are a bit higher for the gluon-gluon fusion processes, and basically coming from the QCD scale variations and from the PDFs, and smaller, at least from what regards the QCD scale, for the vector boson fusion processes. Also, this 8% for gluon-gluon fusion probably is going down with newer calculation. Okay. Then, on top of production, there are decays. So this mass of 125 GeV is very interesting because there are more or less all the possible decays with a significant branching ratio. So the highest branching ratio is in BB bar. That is a very difficult channel to detect. And following that, we have WW and ZZ. And if you go a bit, you look here, you have tau tau. And if you go farther down, you have gamma gamma. That is an important one. And the width of the expected for the Higgs boson at this mass is very small. It's about 4 MeV. So below any experimental resolution. So the first channel I would like to present is the Higgs into 4 leptons. Basically, this is the channel with a very good signal over background ratio. So the main background is standard model for lepton production. And it's a simple analysis. Basically, you calculate the invariant mass of 2 lepton pairs. And of course, what is important is experimentally is to have a good lepton identification and also good momentum resolution to resolve the peak. And this is the measured 4 lepton mass spectrum from Atlas in this case. Here you see essentially there is this peak here that is basically from Z decaying into 4 leptons. Then at high mass you have the opening of the phase space for 2Z production on shell that is basically dominant in this region. And here you have this peak that is the production of the Higgs that goes in 4 leptons. And this is basically a very nice signal over a small background. And using this, here I show the exclusion range produced by CMS, basically an Higgs in the range 114 to 832 is excluded, except in this small region around 125. And you can try to evaluate the signal strength to compare if the number of Higgs that you observe is compatible with the standard model. So the important point is that there is this depends on the mass at which you look. So you can make a plain signal strength versus mass. And so depending on the mass that you choose, you have a different signal strength. This is to be keep in mind for the next, for all the cases where I show a signal strength. In this case, for Atlas, what is observed is 100.44. That means that cross-section observed over standard model cross-section is 100.44 with this error, so it's well compatible with 1. And the same for CMS, it's well compatible with 1. Okay, so the other important channel is Higgs to gamma-gamma. Here, again, one expects a peak in the diphoton invariant mass. There is a background here. This shows the diphoton invariant mass spectrum from Atlas. Here you see the backgrounds mainly. This is jet plus photon. So this includes jets misidentified as photons. And this is the real gamma-gamma production. And you can see, basically, you need a good photon identification to reject jets. And, of course, there is this background that is not directly, cannot be reduced because it's real gamma-gamma standard model production. So you have to try to find a peak on top of a smooth background. So what is important is to have good photon energy resolution, but also angular resolution to get the angles at which are produced the opening angles of the 2 photons. This is done with 2 slightly different approaches by CMS and Atlas, because Atlas has a method to select the hard scattering interaction among the many interactions occurring in the bunch crossing. And while Atlas also exploits the longitudinal segmentation of the calorimeter to point toward the correct vertex. And another important point is what is used in this analysis, but also in the previous one, actually, but is particularly important in the Higgs to gamma-gamma, is the categorization. So you don't do simply an invariant mass spectrum, but you try to classify events based on expected signal over background using kinematics and photon ID variables. So then you can do plots like this in which you weight each event by its signal over sigma plus background and search for a peak. These are the 2 plots from CMS and Atlas. You can clearly see the peaks there. Both have a local significance above 5 sigmas. And if you look at the signal strengths, so the data over standard model rate, you see they are very compatible with unity. Okay. The other diboson channel is Higgs to WW. This is very sensitive at for 130 to 200 GeV. And as in comparison with the previous channels, has the problem that you cannot have a complete reconstruction of the final state because you have the neutrinos that are going away. You have quite large background from standard model WW production, but also from TT bar and Radian. And what one can do to select the signal is exploit the characteristic angular correlation that we have in the production of Higgs, because you have that Higgs is scalar, and so the spin of the two W's have to be back to back, and due to the V minus A decay of the W's, you will have that the two leptons tend to go in the same direction. So the analysis requires two opposite side leptons, missing ET, then categories based on 0, 1, and 2 jets, then topological cuts on the two leptons, mass, PT, phi. And what is very important is that you have to use dedicated background sample to estimate the backgrounds. Use control samples because you don't have a clear peak. So you need a good estimate of the background from data. And when you put all this together, you have a plot like this. This is the transverse mass of the system. You have this distribution. This red is the Higgs signal. When you and this is basically the other WW processes. When you subtract the background, you have this kind of signal. And if you look at the plot signal strength versus mass, you can see that these measurements don't give a very strong constraint on the mass. So you give this kind of shape. So what is done, you take the best mass from the other measurements, and you, for example, 125, and you look at the signal strength at this point. So, and these are the signal strengths from CMS and Atlas, again, very compatible with one, and both the two experiments have significance between 4 and 5 sigmas. Okay, so once you have measured all these three processes, the two collaboration did is to try to get a precise measurement of the mass. So what is important is that the response of the detector are to be calibrated. And this was done really to very good accuracy at the per mil level, exploiting non-dimuon and dielectron resonance from other standard model processes. This is, for example, as a function of PT, the mass scale for muons from Atlas, where you see Z, upsilon, J psi. This is the Z mass spectra from CMS. And compared to Monte Carlo, so you see the calibrations are very good. So what is left is that the final error is basically statistically dominated. And here you have the results from Higgs to gamma gamma, Atlas and CMS, 2 for leptons, Atlas and CMS. So at the end, they are all basically compatible. There is some 2 sigma level fluctuation. And when you combine everything, you get this mass that is 125.09 with something like 0.2 statistical and plus 0.11 scale uncertainty. Okay. So of course, on top of the mass, you can try to measure the width. What we say that the expected width is 4 MeV, so is the experimental resolution of these peaks is order 1 to GeV. So what can be done is only to put upper limits. So at the moment, the upper limits are 5 GeV for Higgs to gamma gamma, 2.6 for Higgs to for leptons, and where you combine, you go below 2 GeV basically. Okay, what you can do is to use a trick, so exploit off-shell production to measure the width. So when you take the Bragg-Wigden of a resonance, you integrate what is in the peak and you look at what is in the tail. Basically, you have that the cross-section in the peak contains the width, the cross-section in the tail doesn't, essentially. So you can try to measure the ratio of production in the peak region and in the tail, and get some limit on the width in this way. And here you see that actually in the width you have different processes that contribute. Apart from the Higgs production, there is the ZZ production that has some interference, and on top there is the QQ bar production of 2Zs that also contributes. And so the analysis is based on ZZ and 2W production, and the results are shown in here. So basically, okay, this explains what I was saying, and this is the limits that are obtained. Basically, the ratio of the limits on the ratio of width of the Higgs over a standard model width is at the level of 5, and very similar. Okay, similar results are obtained by both CMS and Atlas, and in both cases these are a bit lower than what would be expected. And of course, this depends a lot on our assumption of what is the cross-section for the other processes like QQ2 bosons. So it's a bit an indirect measurement, yes. Okay, so what can be done with this sample is also to study spin and CP properties. So studying the kinematics and the angular decays of these three processes, one can measure JPC, or at least test hypotheses that are alternative to the standard model 0 plus 1. So the trick is, for example, you take the Higgs into 2Z, and for leptons, you have many angular distributions that you can do. Looking at each one by itself, you don't see very much ability to distinguish, for example, from the standard model and then 0 minus hypothesis. When you take many of them and you put them together into a multivariate discriminant, you start to see some difference that can be distinguished experimentally. Then you combine the three channels and you get very good limits. So in practice, the result is that everything is consistent with the standard model hypothesis. Spin 1 is, of course, is excluded by the fact that you observe the decay in 2 photons that cannot happen for a spin 1 particle. And the 0 minus 2 plus hypotheses are all excluded at more than 95% confidence level. This is shown in this table. Basically, are the different hypotheses for. In particular, for the tensor hypothesis, you have to choose different models with different couplings to the quarks, for example, because this changed the distribution that you observe. Okay, on top of excluding different particles that are completely different JCP, you can also try to check if there are contributions to the Higgs coupling that are different from what you expect from the standard model. So you can try to write a generic Lagrangian for a scalar particle. Then here you have the couplings that correspond to the standard model Higgs. But then you have other couplings from that are still CP even but are not the standard model 1. And then you have CP odd couplings, for example. So you can, what is done is to try to put limits to these extra couplings. These are plots, for example, from Atlas. Okay, for some particular coupling like this K. And this is a summary from CMS that looks at the different channels. And these A2 and A3 correspond basically to these particular couplings here. And you see that in the end, when you combine all the channels, you have this green line is what is allowed at 1 sigma, and is very consistent with the standard model, basically. Okay. Okay, now we go to the search for decays of the Higgs bosons into fermions. And the most promising channel is Higgs to tau tau. So there is, of course, a large background, particularly from Z to tau tau, and also from die bosons. And in this case, we have low cross-section and large background. So in this search, there is a combination of all the different possible channels, from tau going to leptons, but also hadronic taus. And is very, very crucial for all this measurement, a good identification of hadronic taus. This is, for example, a plot from CMS that show the hadronic taus from Z's, where you see the mass of the visible mass of the tau and how well this is reproduced by the different, by standard model expectation. So the experiments are really good identification for taus. Okay. So so these different production models are combined with using signal over background as in categories as explained below. And the other point is that to reconstruct the mass, in the case of taus, you have escaping neutrinos. So you need some method to exploit the kinematics and the missing energy to reconstruct the mass at best. This is an example of reconstructed tau-tau mass for a cut-based selection, in which you see basically here the Z to tau-tau, and on top of this excess. And when you subtract the excess from the background, you have this kind of thing. So some excess here that is broadly compatible with an Higgs expectation. These are different mass hypotheses for the Higgs. So the results, when you do a full multivariate analysis, in combining the different channels, this is the case of CMS, where you see the results for different channels, and the combination, you have these combined results that are compatible with the standard model and with precision that are, still low. I mean, these sigmas are the 3 to, in this case, 4 sigma level. Yes, so it's basically an observation at the 3 sigma level. Yes. So if we go then to Higgs to BB bar, this is a channel where we have very large cross-section, but also huge backgrounds from QCD. So what is done is that one has to use special production channels, like associated production with a boson or vector boson fusion to increase the signal over background. And there have been many cross-checks in which one tries also to look at the very similar process of VZ production with the Z decaying into BB bar. That is something similar. And here we see, for example, the invariant mass of the BB bar from Atlas, where we see in gray the VZ production, and in red what we expect from Higgs. And this is the associated production. This is the vector boson fusion case from CMS, where you see this bump over a very large background. So again, what is done is a multivariate analysis, and you combine different decay modes, different channels, and you end up with a combined result that so it's basically a signal at the 2 sigma level for the associated production from consistent with the standard model for CMS Atlas, and there is also a result from VBF from CMS that is also there. Okay, so this is what has been observed. Now, all these things can be used to measure also cross-section and compared to QCD prediction. So this is a combined result from Atlas, where the cross-section has been measured and combined between 4 leptons and 2 photons. And this is compared to 2 theoretical calculation. In practical, this is the standard one used in most comparison to the Higgs, and this is a quite recent calculation done at the N3 LO level. So that shows that when you go to this number of loops, basically you have a very small uncertainty from the QCD scale. Okay, the measured cross-section is a bit higher, but still very compatible with the expectation. If we look at differential cross-section, in this case as a function of PT of the Higgs, you see still a very good agreement between data and different calculations. Okay, now the other important channel is the TTH production, where this is important basically because the coupling of Higgs to TT bar is important. This is already accessed in the loops of GG, H, and H gamma gamma, but of course in the loops you can have other contributions, so it's interesting to look at it at the tree level. And here the cross-section is really small, but the advantage is that the signal over background is quite good. So what is done is, again, combining all kinds of decays. And these are results from Atlas only for leptonic decays, where you see different channels from 2 leptons and 3 leptons. And here you have also with 2 hadronic leptons, for example. And this is the combination from Atlas. This is something similar from CMS that includes also BB bar and gamma gamma results. So at the end, the results from CMS is 2.8 plus minus 1. So a bit, let's say, it's 2 sigma higher than the one expected in the standard model. The results from Atlas are compatible within 1 sigma, both with the standard model and the CMS results. So this is something maybe interesting to look in run 2. Okay. So once one has measured all these different channels, what can be do is to trying to put together all these measurements and fit couplings and so on. So what is done is that for each of the measured channels, the data are classified based on the production method using selection dedicated to enhance the signal from a particular production. So these are basically the input that goes into the combination. And when you do the combination, you have basically these results. So in this case of Atlas, you have the signal strength for the different decay channels. So this is the combination in which you look at the decays. So you see all this is compatible with the standard model. If you do an overall combined mu, you get this that is very close to 1 from both experiments. Okay, what is a bit more interesting is to analyze this data in some phenomenal, let's say, in this framework that is called K framework. So basically, the standard model coupling is parameterized with this KF, this K factor that is 1 in the case of standard model and can be different. And one tries to put together all the measurement and measure these different K values. And for example, if one looks at the ratio, one looks at GGH that goes to gamma gamma, measures this combination of factors. So each of the process measures a different combination of these factors, and one can try to extract them, extract the couplings to the different standard model particles, basically. So what is important is that if we assume that only standard model particles enter in the loop, then there are relations that connect the photon and gluon couplings to the other KI. This is the example of the X2 gamma gamma. In particular, in this case, you see that there is a negative interference between the top loop and the W loop that allows also to measure the sign of these couplings. So these are results on these K factors, these couplings, from with the assumption of no beyond the standard model decays and no beyond the standard model particles in the loops. Okay, so you see the precision is, everything is compatible with standard model. The level of precision ranges from 15% to 20, 30%. So quite interesting. Okay, and you can also take these results and put them in this nice, at least propagandistic, let's say, plot where you put the coupling strength as a function of the particle mass, and you see very well that the coupling strength is proportional to the particle mass as expected for the standard model Higgs. Okay. Okay. Another, of course, you can try to fix these groups of these k factors. For example, you can assume that all the couplings to vectors are the same and have the same scaling, and all the couplings to fermions have the same scaling. And this goes to the KV, KF, let's say, plane, where you can see here that, so this is basically, yes, the difference between Yukawa and gauge couplings. And assuming that there are no beyond the standard model contribution to the width and to the loops, you can get these exclusion limits, where you have limits from all the different processes, and this ellipse is the combined limit from Atlas here and from CMS here. This is the best combination. This is the standard model point. Here is the standard model point in the case of Atlas. Both are within 1 sigma. And if you look just, you project this on one of the two axes, you have something like 6% precision on the vector and 14% precision on the KF. Okay, so all these measurements can be used can be used in interpretation on beyond the standard model models. For example, if you take the 2 Higgs models, 2 Higgs doublets models, where you have basically the Higgs plus this extra heavier Higgs, the axial Higgs, and the charged Higgs. So you can see that basically there is a relation between these parameters that are tangent beta and alpha, that is the mixing angle between the two scalar Higgs, and the parameters that we just constrained. So just from this measurement of the different KV, KU, and so on, you can set limits in the plane tangent beta and cos beta minus alpha for this model. And so you see that at low tangent beta, more or less, there is almost everything is excluded except the standard model. And at large tangent beta, okay, you have this region still allowed. And you can interpret this in the framework of the minimal supersymmetric standard model, that is a particular case of the 2 Higgs doublet model. And here, for example, you have the limit on tangent beta versus the mass of the axial Higgs, and you see that for large tangent beta, basically you have a limit of 400 GV, basically, for MA. And this is a plot that basically has been shown in the previous talk before the coffee break. So this exclusion in KF, KV can also be interpreted in terms of these composite Higgs models. So these are in the case of these particular models, basically you can relate psi to these couplings that have been measured. And here you have for different values of psi that you move in this direction in the plane, and basically, okay, this is the region basically allowed, that is around 0.01. This is true that in the case of Atlas we have a fluctuation in the opposite direction. In the case of CMS, this is more compatible. Anyway, we will see in the next round probably. Okay. now, of course, one can use these measurements also to check if there are decays of the Higgs into invisible particles. Basically, one can try to sum up all the observed decay and see if there is anything somehow left. And basically, technically, what is done is one takes the fit that I said before and keeps free the couplings related to the loops, because in this case, we allow for non-standard model particles in the loops. And also, we add a new parameter that is the branching ratio to invisible. And you can fit these parameters and get limits on the invisible branching ratios that are about 30%. Okay. So one can do even more, so look directly at invisible decays. This is done, for example, looking at a Z or a W that recoils against anything, so something missing. So this is missing a T, for example, in the Z, in the analysis of invisible Higgs recoiling against that Z from Atlas. This is the analysis in the vector boson fusion production mode, again looking at missing transverse energy from CMS. And these are the limit that you can obtain for these direct searches that are, okay, a bit less stringent than the one shown before for this case. For the BBF limits, they are again around 30 or 40%. Okay, let's say 50. You can read the numbers yourself. In CMS, combine the direct and indirect limits and obtain again something like 30%. Okay, so these limits on the invisible decays can be, as many interpretations, of course, depending on your favorite model. One is dark matter. So there are these Higgs portal models that somehow predict the coupling of these dark particles to the Higgs. And so you can use, in these models, you can set limits on dark matter. Okay, so this is a dark matter mass. These are the limits under different assumptions of vector, fermion, or scalar. And you see that these limits are very competitive to direct search limits for dark matter produced. Okay, from a, and of course, these are only valid below the 1/2 of the Higgs mass, because you need the Higgs to be able to decay into dark matter states. So just an overview of the next, towards the next LHC years. So LHC run 2, this year we will collect probably about 8 inverse femtobars at 13 TeV center of mass energy. So basically, this will allow to confirm the run 1 results, and will give also some sensitivity to high mass Higgs beyond the standard model. And this is particularly true because here you can see the ratio of parton luminosities between 13 and 8 TeV. You can see that if you stay at the Higgs mass, you have a factor 2. So generally, Higgs cross-section are a factor 2 higher at 13 TeV. When you start to go at 1 TeV, you get factor 10s in cross-section. So for run 2, we expect about to collect by 2018 100 inverse femtobars. So we will have all these channels like tau tau, BB, and observed, probably also TTH at least 3 sigma. We can improve all these mass and coupling measurements. At the end of run 2, the expectation is to have couplings measured at the level of 10%. And of course, if there will be a luminosity LHC, we will be also able to look at very rare decays like Higgs to mu mu, Higgs to Z photon, measure the Higgs couplings at the few percent level, and also probably have an observation of the to Higgs productions. And of course, all kinds of searches beyond the standard model. Okay, this is a projection of what can be the couplings, the precision that we can obtain of the couplings at the end of run 2 and at the end of high luminosity LHC. I don't go into detail because I basically said. The only thing I would like to stress that run 2 has started. We already started to collect data. 8 inverse picomars so far. We have very nice signals. This is Pi0 signal from CMS. This is the dimuon mass spectrum from ASAS, where you see all the standard model resonances. And this also shows that for the Z, for example, we have already very good calibration, very good data to Monte Carlo agreement. So this is very promising. And OK, these are the conclusions that I don't know if I go through. Basically, it's a repetitive. OK, so there is a very clear Higgs boson signal at a mass of 125.09 GeV. The spin 1, 2, and axial scalar hypotheses are basically excluded. We have signals for fermion decays at the 3 sigma levels for tau tau, 2 to 3 sigma levels for BB bar. And we did all kind of fits using sigma cross-section time branch duration for the different channels, and everything is consistent with standard model, but also allow to constrain a wide class of already to constrain some model beyond the standard model. So the run 2 has just started, and OK, we will get probably better mass and coupling measurements. Thanks. Also slower.
Questions? We have time, I think, 5 minutes or so for questions.
Yes.
Myself, if maybe some will come later. Yeah. So you had, just the slide before, you had some data from CMS. So that's good news. That means that they are seeing something.
No, they're saying something. So you know probably that it was this problem with the magnetic field.
Yes, that was
so
what I'm alluding.
By zeros, you don't need the magnetic field.
Okay.
You just measure photons. So
yeah.
Probably you measure them better than with the magnetic field.
Yeah. But is there any news about the problem, or?
Okay, they say that probably they I don't know. This is not official. Okay, I think so. I think they say that probably they will ramp soon, and this will work. It's already working. Okay, you know better.
Okay. So we have the good news. Good.
Okay.
Perfect. Yeah.
Good.
Any question in the meantime, or? Mark? So everybody is happy. Thank you again.
Thank you.